GTA's approach to large-scale hydrogen production by offshore wind and marine energy is development of resilient, EMP-hardened, fail-safe hydrogen grids. This slide shows a cutaway view of a proposed 1 gigawatt GTA offshore wind hydrogen farm. The farm is comprised of 100 10 megawatt offshore wind turbines that power 100 10 megawatt GTA electrolyzers. Each wind turbine electrolysis pair functions autonomously. Loss of one pair does not affect operation of the other pairs. GTA electrolysis systems are anchored at the sea floor, where they leverage ambient cold water and hydrostatic pressure for cooling and first-stage hydrogen compression without a mechanical compressor. Here's an illustrative example of a 10 megawatt GTA electrolysis system that is comprised of 100 kilowatt modular components. GTA electrolyzers contain no moving parts and rarely need servicing. The electrolyte is an aqueous solution of potassium hydroxide. Electricity from the wind turbine is sent to the sea floor via umbilical cables, similar to those developed for the offshore gas and oil industry. Native wind turbine AC electricity is rectified and conditioned for powering the electrolysis array. Desalinated water consumed by electrolysis is replaced by a subsea reverse osmosis water supply system similar to that used in secondary gas and oil recovery processes. However, the demand for water is considerably lower. For electrolyzers powered by a 10 megawatt offshore wind turbine with a capacity factor of 45%, the average daily demand for desalinated water is 800 liters per hour. The peak demand is 1,800 liters per hour. These rates of desalinated water production are well within the capabilities of commercial subsea reverse osmosis systems. GTA electrolyzers are constructed from split polyethylene pipes that are fabricated using rapid mass production manufacturing techniques, including thermoplastic injection molding. Polyethylene is a material with near perfect stability in seawater. Potassium hydroxide is a thermal stabilizer for polyethylene. Hydrogen and oxygen gases are expelled from their respective compartments by internally generated pressure and vent into separate exhaust gas pipelines as shown. Back pressure regulators, located downstream from the electrolysis system, regulate the internal pressure of the system. The pilot pressure for the regulators is the ambient seafloor hydrostatic pressure, wherein pressure-balanced electrolysis of water is performed. This slide is Figure 3 from the publication Hydrogen at Scale, Key to a Clean, Economic, and Sustainable Energy System from the Electrochemical Society Journal Interface. Sunita Satyapal is the director of the U.S. Department of Energy's Hydrogen and Fuel Cells Technology Office. Neha Rastagi is a program manager in the office. Brian Pivovar is a staff member at the National Renewable Energy Laboratory and manager of DOE's Hydrogen at Scale program. The bottom rows of the chart show cost elements that contribute to the cost per kilogram of hydrogen produced by electrolysis of water. These are electricity source capacity factor, the cost of electricity, capital cost for the electrolysis cells, and conversion efficiency of electrical energy into hydrogen energy. The right-hand bar shows a price of $1.95 for hydrogen produced by the steam methane reforming process, also known as SMR, or gray hydrogen. The second and third bars show that with a 40% capacity factor, a cost of electricity of 1 to 2 cents per kilowatt hour, and a 60% conversion efficiency, a capex cost of $100 per kilowatt will become cost competitive with gray hydrogen. Our calculations of materials cost and estimate of manufacturing cost suggest that GTA electrolyzers come within striking distance of $100 per kilowatt. This slide provides an estimate of the materials cost of a 100 kilowatt modular component for the 10 megawatt electrolysis system shown in the previous slide and the inset. GTA electrolyzers are constructed using commodity materials only. These are polyethylene, porous polyethylene, silicone rubber, nickel, and corrosion-resistant steel, such as 316 stainless steel. The component dimensions were calculated by linear extrapolation of the data obtained with the GTA laboratory prototype. The table itemizes the components of a 100 kilowatt module, including component material, number of components, pieces required, component weight, cost per weight, and calculated component cost. We estimate a per module electrolyzer materials cost of $14 to $29 per kilowatt. The calculation excludes the gas pipeline network that connects the modules shown in the slide. GTA electrolyzers exclude platinum group metals. The housing components are fabricated from thermoplastic polymers such as polyethylene. The components possess simple geometric shapes with few cavities. Fewer cavities require less tooling and lowers injection mold costs. Accurate parts with pristine surfaces can be rapidly produced. No additional finishing steps are needed. No other rate of electrolyzer production comes close to thermoplastic injection molding. Rapid electrolysis manufacturing is a techno-economic requirement for gigawatt-scale green hydrogen production. 4 approaches to electrolytic hydrogen production powered by offshore wind or ocean energy have been proposed. The first is subsea electrolysis. The second is placing an electrolysis system on a platform that is fastened to the tower of a wind turbine where the platform is elevated above the splash zone. The third is exporting the wind or ocean-generated electricity to electrolyzers that are housed on islands or ocean platforms. The fourth is exporting the wind or ocean energy-generated electricity to electrolyzers that are housed on shore. The tables on this and the following slide compare performance metrics for 2 approaches that eliminate high voltage cables and large power transformers. The first approach is GTA subsea electrolysis. The second approach is offshore platform construction that is fastened to the tower of the wind turbine, is positioned above the sea level splash zone, and supports the PEM electrolysis system. GTA subsea electrolysis includes 2 levels of fail-safe protection against subfreezing weather. First, the temperature of deep cold water at the sea floor is 3 to 4 degrees Celsius and never freezes. Second, the freezing point of 30% potassium hydroxide is negative 60 degrees Celsius. Therefore, GTA electrolyzers contain 2 levels of fail-safe protection from periods of unscheduled downtime during subfreezing weather. The most common cause of unscheduled downtime is unfavorable weather conditions that prevent power generation by the wind turbine generator. The platform-mounted PEM electrolyzers circulate high-purity water that freezes at 0 degrees Celsius. When fastened to the platforms above the splash zone as currently proposed, they can be exposed to subfreezing temperatures. During subfreezing periods of shutdown, they must have backup power to maintain operation of essential systems and to avoid freezing of the electrolysis systems. Positioning the electrolysis system on a platform above the splash zone raises the center of gravity, requiring the ballasting system and substructure dimensions to be modified to ensure the turbine remains stable. Codes and regulations for offshore wind turbines will need to be rewritten to accommodate the new inertial, aerodynamic, and hydrodynamic forces caused by the platform mounting. Fastening the electrolysis system to the tower of a wind turbine breaks the aerodynamic flow symmetry around the tower. The electrolysis system and solar panels add a 360-degree sail-like structure that subjects the tower to non-productive forces and alters local wind flow patterns. Turbulence, eddy currents, and cross-flow that are generated by these structures will mix and interact with the overhead wind directed at the turbine blades. The coupling of wave motion with the floating wind turbine system exerts inertial forces on the tower and turbine by repetitive acceleration and deceleration. These forces are amplified by the presence of the platform equipment. Additional techno-economic advantages of subsea electrolysis are shielding from lightning strikes, falling ice from the wind turbine blades, ice flow impacts, the destructive power of high waves, and electromagnetic pulse, also known as EMP. Ambient hydrostatic pressure and cold water at the seafloor are used for first-stage gas compression without a mechanical compressor and for system cooling. Subsea electrolysis systems do not need lift pumps to bring water out of the ocean and transport it to elevated decks that are positioned above the splash zone. Subsea electrolysis by electrolyzers anchored at the seafloor is the universal solution to all methods of offshore wind, ocean thermal energy conversion, and marine hydrokinetic energy conversion devices such as waves, tides, and current. Other competing approaches were analyzed by GTA and deemed to be less attractive based on the unfavorable capex and opex burdens associated with large power transformers, high voltage cables, and offshore platforms. The experimental setup for technology validation of a GTA working prototype at the National Renewable Energy Laboratory is shown here. The electrolyzer stack and sample cylinder are labeled. The SAE J2719 test protocol for fuel cell grade hydrogen was used for the validation project. The units for the numbers in the two data columns are parts per million. The center column is the SAE target. The right-hand column is the measured value. GTA electrolyzers use a simple design and are constructed mostly from plastic, yet they produce hydrogen with a native purity of 99.65%, a value of sufficient purity for most present-day industrial applications such as ammonia production. A single oxygen removal step lowered the oxygen content to 9.4 ppm, a value close to the SAE 5 ppm target. The other impurities complied with the SAE standard, with the exception of water vapor and CO2, for which no removal step was performed. GTA electrolyzers are designed for operation at the sea floor, where ambient cold water and hydrostatic pressure are leveraged for cooling and first-stage pressurization without a mechanical compressor. This slide shows ascending and descending current voltage data for a GTA electrolyzer that is operated at 250 psi or 17.2 bar. This corresponds to an ocean depth of 525 feet or 160 meters. The steel plates that were used to buttress the plastic housing are the dark bookends seen in the photo. Each data point represents a steady-state dwell time of 10 minutes. Depending upon the availability of wind energy, we envision cell operation between 1.9 and 3 volts, corresponding to cell efficiencies of 78% and 49% respectively, with a target efficiency of 60%. GTA subsea electrolyzer technology has been peer-reviewed and vetted by respected third-party reviewers. A TRL-4 working prototype of a GTA electrolyzer was validated at the National Renewable Energy Laboratory. GTA received an Innovation Award at the 2020 Tech Connect Innovation Summit. GTA technology was reviewed by the U.S. National Committee for the Ocean Decade, a committee within the U.S. National Academies of Sciences, Engineering, and Medicine, and added to the Ocean Shot Directory. Anchoring electrolyzers at the seafloor is the quickest way to jumpstart large-scale offshore wind hydrogen production because each unit operation is already being performed by the offshore oil and gas industry, albeit in a different context. It's also the quickest way because no changes to the engineering standards for offshore wind turbines such as hydrodynamic loading and inertial forces are required. GTA electrolyzers are buoyant. They can be manufactured on shore, towed to their designated sites, and pulled into place by pre-positioned installation equipment. The international workforce of the offshore oil and gas industry will facilitate the transition from offshore natural gas production to offshore 100% green hydrogen production. GTA is a prototype engineering company with sufficient resources to elevate its technology to TRL6. We welcome inquiries from investors and developers with the interest and resources to advance the technology to TRL9. Thanks for listening.